Hello and welcome to part 2 of our lecture on thin lenses. In this part, we're going to go over some examples, starting with example 1. So in example 1, we're told that a lens maker wishes to design a meniscus lens with curvature on the side of the incoming light of R1 equals 14.5 centimeters and curvature on the side of the outgoing light of R2 equals 8.65. Okay? And so those are the two sides, right? So essentially it's saying that those are the two sides of our lens. But notice that they both have positive curvature. Since they both have positive curvature, what we're actually talking about is two curves that both point to the right. So you can think of one circle as having, that would be the radius with R1, which is 14.5, and then we have a smaller circle of radius 8.625, so something like this, okay? So this is essentially the two circles that we're using to cut to make our meniscus lens. So in effect, what we're going to do then is shave away the rest of the circle until we get something that looks more like a lens. Okay, I can then bring the two halves closer to each other, like so, and we've got ourselves a lens that is a meniscus lens. Okay, and that's just the name for a lens that isn't like kind of curved inwards like the typical diverging lens that we saw, and it doesn't look like a kind of like an eye like the converging lens. All right, so this particular kind of cut is called meniscus. You won't be responsible for that term, but that is the term. Okay, so just looking at this lens, we should have an expectation about whether it's diverging or converging, which we're asked in part A, but I'll show you where the number comes from. So what is the focal length of this lens, and is it converging or diverging? Okay, so we just need to solve for f. Okay, I do want to draw in the two radii, so let's go ahead and do that real fast. So we'd have, so for the first one, we'd have our R1 value. All right, so this would be R1. And I know it has to be curved that way because it's going to be because it's positive and it's on the positive side. Okay, and then over here, we'll make this R2, so something like that. Okay, because we know R2 is significantly smaller. All right. Okay, so what's going on then? Well, let's go ahead and plug in for the lens maker formula. So we have 1 over f equals n minus 1. And we're told that n is 1.5 for certain types of glass. That's a good number. And then R1 over R1 plus 1 over R2. Excuse me, minus. Notice the minus means that the order really matters, right? So we have to always have R1 be the one that's on the left, and R2 be the lens that's on the right. Okay? So then if we then solve for f, we're then going to get that f is 1 over n minus 1. I'll plug in the numbers here. So that'd be 1.5 minus 1. And then 1 over R1, which is positive, and that's our 14.5. I'm just going to leave everything in centimeters. And then 1 over our 8.65 centimeters. And then I'll raise that whole thing to the negative 1 power. Okay? So let me plug in my numbers here. So 1 divided by 1.5 minus 1, which of course is just 0.5. Okay? So I get negative 42.9 centimeters. Okay? And the negative tells me it's a diverging lens. Okay? Because it can't be a positive lens and have a negative focal length. But we kind of knew it was going to be a diverging lens because if we look, it's thinner at the middle and thicker at the ends. So it meets the always true criteria of what a diverging lens looks like. If it's thinner in the middle, that has to be a diverging lens. Okay, so now we're going to use that diverging lens for parts B and C. So for B, if an object is placed on the side of the second focal point at a distance of 7.7 centimeters from the lens, where is the image located? Well, on the side of the second focal point would be this side over here, because since it's a diverging lens, we know that its focal point, its actual focal point is going to be over here on the negative side because it's diverging, and we know it's going to be pretty large because it's got a very large focal length compared to its 2 radii. So we're going to put it anyway. So we put that object at 7.7. So that's going to be our S. Let me go ahead and draw that in. So we have an S over here. And that's a value of 7.7 centimeters. Okay. And then we just want to solve for S prime. So we'll use the lens formula, the thin lens formula. 1 over F equals 1 over S plus 1 over S prime. So then if I solve for S prime, that's simply going to be 1 over F minus 1 over S to the negative 1 power. Okay. So then in this case, then I'd have 1 over negative 42.9, again leaving in centimeters, and then minus 1 over S. Now S is positive, it's always positive, and that's the 7.7 centimeters here. And we'll raise that whole thing to the negative 1 power, and that's the way we got S prime by itself, by taking the reciprocal of both sides. Okay, so I have 1 divided by negative 42.9, take the unrounded value in my calculator, and 1 divided by 7.7. Okay, raise the whole thing to the negative 1 power, and then we have negative 6.53. 53 centimeters. Okay, so what does that tell us? Well, it tells us how far the image is. It tells us that our image is pretty close to our object itself, and it also tells us that it's going to be on the same side as the object because it's negative. And so again, I keep referring to the negative and positive, but this is just a reminder, right? Anything on this side other than S is negative. Anything that points to this side is positive, which is why our R1 and R2 are positive. Okay, so then S prime is going to show up right here. So let's draw that in. All right, so that's our S prime. Looks good. Now, what about our magnification? Because we're asked about that as well. Okay, so in part C, we want to solve for the magnification. Should be easy since we have everything together. Our magnification is just negative S over S prime. Okay, or S prime over S, excuse me. Of course. And so we have negative and then negative 6.53 centimeters for the S prime length, the distance to the image. All right. And then in our denominator, we'll simply put the distance to the object, which is our positive 7.7 centimeters. So then we'll have a negative, which is going to cancel out, which is going to tell us that our image is virtual and upright. But of course it is, because it's a diverging lens, and diverging lenses can only create virtual upright images. So we get positive 0.85, or 848 actually. So 0.848. And again, note that it's positive, which tells us it's virtual. And the numerical value, 0.848, tells us that our image is a little bit smaller than our object. Right? It's only 84.8% as tall. Excellent. Okay, so there it is. We made a lens, given 2 radii, and an index of refraction. We then use that lens to find that focal length, because really the lensmaker formula gives us that focal length. And once we know the focal length, then we can put an object anywhere and find out where the image will be. And then once we know where the image is, we can then find the magnification. So you see how that information, how one bit follows from another. Okay, so question 1, I really want you to do that for practice. I'll post my answer for it later, but it's a great way to get some practice with ray drawing. Draw the 3 principal rays for both cases. And for you have a converging lens and a diverging lens. And I gave you the cases that I didn't cover on the previous page, on the introduction and key terms page. Okay, let's look at example 3. So example 3, a stamp collector uses a magnifying lens that sits 2 centimeters above the stamp. The magnification is 4. What is the focal length of the lens? Okay, so that's interesting, right? Because this is you might notice the magnification, and you might think, well, then what is the particular value of this magnifying glass? Well, let's see how we do that. So in this case, we'd start with the magnification formula, negative S prime over S. Okay, we know one of those values, right? We know that the magnifying lens sits 2 centimeters above, right? Now we don't know where S prime is, right? We don't know where that virtual image is showing up, but we can go ahead and solve for S prime. So then S prime is just going to equal negative m times s. Okay, so we have negative m multiplied by s. Okay, and so then that's going to be, let's see, oh, we don't, oh yeah, we do know our magnification nodes. Forgetting there, so we'd have negative 4 times s, which is 2 centimeters. All right. So that tells us that our s prime is negative 8 centimeters. Okay, so that's this value right here. Why is it negative? Because it's on the same side as s. Oh, that makes sense, right? Because that's certainly the convention that we keep referring to. So anything on this side is negative. Anything up here is positive in this vertical case, the way it's drawn. Notice that the virtual image is underneath the table. That's just where it appears to be located. That's where your eye is going to recognize it, and that's where you're going to see a bigger object, okay? Because it's going to be 4 times bigger, which we know from the magnification value of 4. So now that we have the location of s prime, we can then use that to find f. So then we go to the thin lens formula, and then we simply solve for f. All right, so it's going to be 1 over s, which we know to be 2 centimeters, and then 1 over s prime, which we know to be negative 8 centimeters. Okay, and the whole thing raised to the negative 1 power, so that we got f by itself. So I have 1 over 2 plus 1 over negative 8. Okay, and so then I get a focal length of 2.6, well, 2.7, because we only had one sig fig, but we'll pretend like we have 2. So a focal length of 2.7 centimeters. Okay, so does it make sense that it's a positive focal length? Absolutely. It's a converging lens. Look at the picture. But also think about what it's doing. It's creating a virtual image. Well, diverging lenses create virtual images, but so can converging lenses. However, notice that the converging lens is creating a virtual image by putting an object within the focal length. On the introduction page, on the key terms page, the example I showed was an object that was outside the focal length. In that case, the image was real and inverted and was on the opposite side of the lens. Ah, okay. So a magnifying lens is using a converging lens, but putting an object inside the focal length. Indeed, here, we put an object 2 centimeters away from the lens, the focal length is a little bit further out. Okay? And magnifying lenses work best when the distance to the object is pretty close, just a little bit within that focal length. In this case, it's 0.7 centimeters within, or 7 millimeters within. And but kind of getting a magnifying glass to work just right is kind of fine-tuning that relative proximity. Okay, so good example here, working with a converging lens and working backwards from magnification to find focal length. All right, so I have one more example I want to show you. First a question, then one more example. So in this question, I thought it would be a good idea to just fill out this table and make sure that we understand all the information here about the sign conventions. So here I have a converging lens mentioned twice. Okay, and then I have a diverging lens as well. Okay, so in the first case, we have an object outside the focal length of a converging lens. So what type of object is created in that case? Well, we know it's going to be real, right? Because we saw that on the first page. And we know it's going to be, well, upright or inverted. We know it's going to be inverted. Okay? We know that the side of the lens it's going to show up on is going to be the opposite side. Okay? And we know that it's going to be larger, right? So take for example, this example here. We had our real inverted image was larger than the object, okay? Okay, so that is using a converging lens by placing an object outside the focal length, okay? So we just saw one now where we had an object that was placed inside the focal length. So you can kind of get an idea about how that would play out as well. So I think I want to leave the rest of this table for you to fill it in. I'll post the notes after the fact, but I think it would be very useful to make sure that you kind of, by seeing an example of me filling in one row, how you can fill in the rest of the information, make sure you understand it. Okay? Speaking of which, there's of things for you to do. You have example 5 and question 3. So you're just identifying which of these lenses are converging and diverging. You can think of the lens maker formula, or you can just think of the general rule about whether it's thicker or thin in the middle. All right, but make sure kind of you can have flexibility with your thinking there, that there's consistency by using the lens maker formula or the general rule. So the last thing I want to show you is the final example, example 6. Okay, because this is the one example we have of using 2 lenses. Also, your post quiz has a problem that has 2 lenses being used together, or in that case, a lens and a mirror being used together. Okay. Or was it 2 lenses? Anyway, so let's take a look at this example. So 2 thin lenses, one a converging lens and the other diverging lens, are separated by 1 meter, as shown, along the same principal axis. Right, they're lined up. The magnitude of the focal length of the converging lens is 25 centimeters, and the magnitude of the focal length of the diverging lens is 40 centimeters, so a value of negative 40. An object 8.25 centimeters tall is placed 35 centimeters to the left of the converging lens. Where is the final image produced by this combination of lenses? Give your answer relative to the diverging lens. All right, so this will be fun. So I'm going to go ahead and draw the object in. So we know that it's going to be 35 centimeters to the left of the converging lens. Okay, so it's going to be right here. I guess it's already shown. Never mind. Okay, so that's our object. I thought it was another axis. It threw me off, but it's labeled as object. So then what's going to happen? Well, we want to think about what is our focal length, right? So for the converging lens, so I'm going to label these as 1 and 2. That's a nice thick, right? So that's lens 1 and lens 2. So for part A, to get this started, we have that f1 is 25 centimeters. Okay, so 25 centimeters. Meanwhile, f2 for the diverging lens, that one is negative 40 centimeters. And here I'm putting the negative just because that's what I'll be using in the lens formula. Now, so right away, I have an intuition about what I'm going to expect to happen in the solution as I use the lens formula, is that my object here is, well, it's outside the focal length of lens 1, right? Because f for lens 1 is a little bit shorter, right? It doesn't go all the way out to there. It only goes out to this point right here. So this is our f1. And if the object is outside of f1, it should be creating a real image. And that real image is then going to get picked up, in a way to speak, by the diverging lens. And that diverging lens will make an image from the real image that the converging lens created. Okay? Okay, so let's go ahead and then find the location of what I will call S prime. Okay, I'm going to call it S prime 1. So we'll say thus, the image created by lens 1 is, okay, well, I'd have 1 over S prime equals 1 over F minus 1 over S, this is with a slight modification. And so then my location of S prime is then going to be 1 over my 25 centimeters. Okay, that's F1. Okay, and these should all be 1s. Okay. All right, and then minus 1 over S1. Okay, so S1 was the 35. Good, looks good. Okay. Okay, so we can see we're going to get a positive value here because this is a smaller number because it has a bigger denominator. And so let's take our 1 over 25 minus 1 over 35, raise the whole thing to the negative 1 power. All right. And so then what do we get? So we get 87.5. Okay. So 87.5 centimeters. Okay. So that is our S1. That's the location of our first image. So that's going to be over here. Try that a bit better. There we go. So that right there is S prime 1. Okay. So now that image is going to become the object for the diverging lens. And this real image becomes object for diverging lens. Okay. And so what that would look like then is then we would simply use the lens formula again. I'm going to use the given focal length for the diverging lens, and then I'm going to find S2. Okay? So I'm going to have 1, I'm just going to write out the lens formula. So I'm going to have 1 over F2 equals 1 over S2 plus 1 over S prime 2, with S2, so object 2, equal to S1 prime. Okay, so in other words, this was the image from the first lens becomes the object for the second lens. Okay, and so then if I go ahead and solve for S2 prime, I'm then going to have 1 over the focal length of the diverging lens, so negative 40 centimeters, and then minus the S2. Okay, so minus 1 over, well, it's not going to be 87.5 though, is it? It has to be 1 meter minus. So I shouldn't say that they're exactly equal to each other, so I'll clarify that. It would be with S2 equal to 1 meter minus S1 prime. Okay, and so when we do that, if I take 100 centimeters and minus the 87.5 that we got, then I get 12.5 centimeters here. Okay, and it's a positive value, so 12.5 centimeters because it's an object, and object lengths are always positive. Okay, so that's going to be my S2 prime. All right, and then give your answer relative to the diverging lens. Okay, so this actually will be relative to the diverging lens, so this will be our final answer. Okay, so I'm just going to set this up in my calculator. I got 1 divided by negative 40 minus 1 over positive 12.5, and then the whole thing raised to the negative 1 power. Okay, so I get negative 9.52. 52 centimeters. Okay, so that is our answer. Or another way to put it is that, in fact, here, I will write it this way. So we can say, thus, the final image is 9.52 centimeters to the left of diverging lens. Okay, and because we know it's to the left because I got a negative value, and that negative value tells me it's on the same side as S, well, there was S, which means that the image is just going to be a little bit closer, right? So essentially it's going to be right in that region. We can go ahead and label that. So then this right here is going to be the final image location. That's going to be S2 prime. S2 prime. Okay? Looks good. All right. So compared to the object, is the final image upright or inverted? Is it real or virtual? Okay? So let's think about what we know here. We know that it's definitely a virtual image. We know it's a virtual image because we had a real image created by the converging lens. The diverging lens can only create virtual images, so it's going to create a virtual image. And we also know it's a virtual image because if we were to take a look at the magnification, it would give us a positive value, telling us that it's upright. But here's the thing. It's upright relative to the object. But let's think about it. The object was the image that was created, all right? So if I was to go in here and actually kind of draw in the objects, so this is the first object, then the second one that's going to be created would be right here. That one would be upside down and is actually going to be larger, so it'll be something like this. And then the virtual image that's going to be created would be non-inverted. It'd be upright, but be upright, again, as I said, relative to the object. But this now is the object from the point of view of the second lens. So to keep it upright means keeping it flipped. So it's actually an inverted virtual image. And the only reason for that is, again, because the object was inverted. And inverted. And I'll just say, because the object was inverted. And again, because the object was the image created by the converging lens. So definitely kind of interesting answer there. And the same sort of thing you should be thinking about in the post-quiz. Okay, so that concludes this last example. So hopefully seeing some practice as well as some conceptual ideas of these lenses in combination or individually with or without the lens maker formula brings these ideas